Welcome to Stickball Chemistry. Today we'll be discussing types of intermolecular forces and their macro effects. First, the word intermolecular can be split into its subparts. Inter, between, and molecular molecules come together to mean forces in between molecules. Intermolecular forces are important because the interactions between molecules affect the ways macro objects interact. Freezing and melting points, for example, are determined by the strength of the intermolecular forces inside the substances. Let's now go more into depth on the types of specific intermolecular forces out there. To begin, London dispersion forces are the most commonly experienced forces. Any two molecules, polar or nonpolar, are drawn together by London dispersion forces. When we take a closer look at molecules, we see that atoms in the molecules have electrons whizzing around. More specifically, the electrons are whizzing around relatively randomly. The significance of the randomness is that at certain moments, groups of electrons may shift to one side, causing an instantaneous dipole. London dispersion forces come into play when a negative instantaneous dipole is attracted to a positive one. Here are some important things to remember about London dispersion forces. Since London dispersion forces results from the sway of electron clouds, it applies to all molecules. And out of all the forces, this force is the weakest. But this force can become significant when electron clouds are larger. With larger electron clouds, the influence of the electrons shifts become more prominent, meaning the London dispersion forces also become stronger. London dispersion forces may be discrete, but they're definitely important.
So the next thing we're going to discuss is dipole forces, which depend on polarity of molecules, which depend on electronegativity and molecular geometry. Electronegativity is basically how much an atom wants electrons. As seen in the OH configuration below, O is more electronegative, pulling more electrons to its side, creating a dipole for a molecule. We can explain this using physics as well and net forces. Think of a horse-drawn carriage. On one side there's a strong horse/more electronegative atom which pulls stronger towards its side, creating a net dipole for the carriage/atom. Now, how does molecular geometry affect polarity? Well, depending on the shape of the molecule, aka tetrahedral T-shaped bent, the molecule can be polar or nonpolar. We can use horses to see this again. As seen below, the horses are configured in a trigonal pyramidal position. When they all pull in their respective forces, there's a net force downwards. So dipole forces, there are two main types. One is dipole-induced, which has an originally nonpolar molecule, and a dipole force. So the dipole is when two dipoles match together, opposites and attract, and dipole-induced dipole is when a nonpolar molecule is induced. Dipole forces tend not to be too strong. What tends to be a stronger bond is the hydrogen bond. For hydrogen bonds, remember Han or H, O, and N. Not HONO, Han. O and N because they're very electronegative. Now add in an F because hydrogen bonds are fun, and you're left with F, O, and N. All three very electronegative atoms, decreasing in electronegativity in the order seen. Now, basically, what hydrogen bonds are just very strong dipole forces due to high differences in electronegativity between H and F, H and O, and H and N. So therefore, if you see any of these three on a molecular structure, you know it can form hydrogen bonds. Hydrogen bonds also explains why water has such a high relative boiling point to other liquids. The last two types of forces we're talking about are ionic and metallic bonds. Ionic bonds exist between a positively and negatively charged particle. The nature of the bond can be explained by physics using Coulomb's law, K, Q1, Q2 over R squared, where Q is the magnitude of the two charges and R is the distance between the charges. Now, when these two charges come together, they form one of the strongest bonds known to chemistry, known as the ionic bond. Essentially, metallic bonds are the same thing. You have positive ions floating in a sea of electrons held together by electrostatic forces that also follow Coulomb's law. Metallic and ionic bonds tend to be the strongest bonds known to chemistry. However, they are governed by the distance between the charges and the respective charges' magnitudes, as seen by Coulomb's law. If you increase the charge magnitude or decrease the distance between the charges, the force goes up.
Next, we will examine how intermolecular forces are able to affect our daily lives. One key role that intermolecular forces play is in adhesion and cohesion. Adhesion is when two different molecules attract, while cohesion is when two similar molecules attract. An example of adhesion is when we read a measurement by looking at the meniscus. But why do we do that? Well, water and other polar molecules tend to adhere to the surface of glass. This is because glass's surface forms silanol. Silanol's hydroxyl group can form bonds with the solution, like it forms hydrogen bonds with water. Moving on to cohesion, water by itself forms hydrogen bonds. So when placed on a penny, water bubbles due to the cohesion between water molecules, allowing it to slightly hold its shape.
Thank you for watching. This has been Stickball Chem.